Hello, I'll be discussing design and estimation for the population prevalence of infectious diseases with limited testing resources. This is joint work with Alyssa Mikituk, Vicki Lancaster, Josh Goldstein, and Sally Keller, and we are from the Biocomplexity Institute at the University of Virginia. So, being able to obtain accurate and fast current status prevalence estimates during infectious disease outbreaks is crucial to inform public health decisions. Being able to answer questions such as how many people have been infected, how many people are infected, and where they're located are crucial bits of information for policymakers as they make decisions. And there's no better exemplar of this than the past year and a half during the COVID-19 pandemic. And of course, as we saw there, limited testing resources can derail accurate estimation, especially in the early stages when the speed of the disease outpaces resources. And what often happens in these situations is that the testing is really focused on symptomatic individuals and frontline workers. And inferences based off of these testing situations don't really generalize beyond the tested population. So one way to be able to get unbiased estimates of prevalence are through population representative biomarker surveys. But of course, these are practically very difficult to conduct, especially in the United States, where it's very difficult to get willing participants. However, 3 states, Indiana, Connecticut, and Ohio, were able to conduct statewide surveys. And in addition, several universities conducted semi-regular representative testing. So in thinking about the survey designs, there are two common and popular building blocks for populations with heterogeneous disease risk. The first is stratified random sampling, where the population is stratified into separate strata and sampling is performed within each of the strata. And this is really reasonable for concentrated populations, for instance, college students on a campus, and of course is statistically efficient. The other is multi-stage cluster random sampling, where the population is separated into clusters and the clusters themselves are sampled. And within those clusters, you could do some sort of random sampling, including stratified random sampling. So this is a more efficient use of time and resources generally for larger populations that are more spread out. And of course, the exact choice of design is going to depend on the population under study and can really be made as complex as needed. So along with those design considerations, there are a number of estimation challenges that present itself in these types of settings. The first is that of low population prevalence. So especially in the early stages, the prevalence in a given population can be quite low, which necessitates large samples for reasonable inference. And in addition, we have imperfect tests, which lead to misclassification bias. And luckily, there are a number of methods proposed to address misclassification bias, including the EM algorithm, Bayes methods, among others. And these first two challenges are really exacerbated by the fact that there are often limited testing resources. And so one approach that's been proposed during the COVID-19 pandemic has been to use pooled sampling, pool testing, where you pool samples together and test them together to really use the limited resources as efficiently as possible. And so to put all this together, we use a model-based survey analysis, which is known as multi-level regression and post-stratification, or MRP for short, to basically address these challenges and also adjust for the survey design and any differences between the sample and the population of interest. And so at a high level, this is really composed of two different parts. The first is multi-level regression. And this involves fitting a model relating the survey outcome to covariates and all survey variables that you would adjust for in any design-based analysis to estimate the prevalence in each post-stratification cell. And what this really does is give you stabilized small area estimates for these subgroup cells. And then once we have those estimates, we can then post-stratify, which involves averaging these cell estimates weighted by the population cell count. And this adjusts for any differences between the sample and the population. And so this model-based approach is really nice in that it's very flexible, and it's flexible enough to be able to address the challenges that I just previously mentioned in one nice framework. So to give you an example of how this would look, here's a very basic multi-level model. And so, consider an example where the population of interest is the students on a college campus, and we utilize pooled testing and as well as stratified sampling to select the students to be tested. And so the students are selected based on stratified random sampling, based off of the building that they live in and the school that they study in. So how this would look is given here. So we have K, which is the number of positive pools that test positive, is distributed binomially with n numbers of tests and the probability of a positive pool given by P underscore pos pool. And down here, you see that this P underscore pos pool is a function of the true prevalence P, the sensitivity, specificity, as well as C, which is the size of the pool. And here we assume that the prevalence is given by an inverse logit function involving beta naught, the intercept, random intercepts for the building, the school, and the age, as well as covariates at the geographic level for building and school. And so to finish out this model, we would have some sort of reasonable prior distribution specification, and ideally this would be based on some prior knowledge or maybe some previous seroprevalence studies. But here I've just given one example. The coefficients are all normally distributed. The random intercepts are also normally distributed around 0, and their standard deviations are have a truncated normal distribution prior. And so the idea is that then once you specified all this, you would then fit the model to get estimates of all these parameters. And what you do with those is then post-stratify. And so to see how this works, we can represent the population prevalence, P, as this average of the cell estimates P sub j, weighted by the cell counts N sub j. And so here, P sub j is a true prevalence in each of the cells J. And so our estimator, the post-stratified estimator of the population prevalence, takes the exact same form where we replace the truth with the estimated prevalence in cell J from our model, from the multi-level model. Okay, so here I present a simulation study using these models. So for all settings, the true population prevalence was considered to be 0.5%, 1%, 2.5%, and 5%. And the true sensitivity and specificity were set to be 0.95 and 0.995 respectively. And so for this simulation, I considered two design setups. The first is stratified random sampling. And for here, the population was considered to be 20,000. And I considered 200, 400, and 600 tests along with pool sizes of 5 and 10. The other design that we considered was multi-level, multi-stage cluster random sampling, where the population size is 200,000. And we considered 400, 800, 1,200 tests with pool sizes of 5 and 10. And so as to how we generated this data for the stratified sampling design, we assumed that the prevalence was generated by this inverse logit function, where we have the intercept term, we have random intercepts for the geographic stratification variable, race, age, covariate for gender, as well as a geographic level covariate. And so the sampling was done by stratifying on this geographic variable, and within those geographies, we would take a simple random sample. For the multi-stage cluster design, the prevalence form looks very similar, except the geographic variable is replaced by the cluster. And so here the sampling is done by sampling the clusters themselves. And then within those clusters, we utilize stratified random sampling stratified by age. And so here I'm presenting some results for the stratified random sampling case where the prevalences are 0.5% and 1%. So this is really the the extreme low end of what the true prevalences could be. And we present the point estimates as well as the 95% shortest posterior intervals for each of these settings. And here we vary the number of tests from 200 to 400 to 600. And we can see that even at the lowest number of tests, 200, when we have no pooling, which is given by the blue results, we can see that we're still doing pretty well on bias. We're relatively unbiased. And here the posterior intervals are pretty wide, but again, that's to be expected given the level of uncertainty in this estimation problem and how low the prevalences are. And as we increase the number of tests, we maintain estimates that are nearly unbiased and have much tighter posterior intervals. And in addition, as we stay at the number of tests but increase the pooling size, we actually do much, much better in terms of efficiency, and we still maintain unbiased estimates. And this is true of both true prevalences, 0.5% as well as 1%. So these are the results for the same settings, but with the true prevalences at 2.5% and 5%. So these are slightly more reasonably high prevalences. And the story here is relatively similar. So again, as we increase the number of tests, we get more efficient estimates, but even at the lowest number of tests, we're still doing quite well with posterior intervals that are reasonably wide considering the amount of uncertainty that we have. But as we use pool testing, we actually do much, much better without losing much in bias. These are the simulation results for multi-stage cluster random sampling, again, starting with the low end of prevalences with 0.5% and 1%. And here we're considering 400, 800, and 1200 tests. And again, at the very low end, when we have 400 tests and a prevalence of 0.5%, we're still relatively unbiased with our estimates. The uncertainty is definitely large, but again, very reasonably so. And once we add the pool testing in, we can do much, much better. And again, this is the same sort of situation with the larger prevalences. We see the same story here. So I just want to end with a little bit of discussion. So for the proposed method, there are a couple of key choices that have to be made. The first is, of course, one of the most important. We have to define the population of interest. What is the study population? And then develop a sampling design to actually select a representative sample from the study population. And so this is going to vary wildly depending on the practical constraints, the population, the amount of resources. And so, this is definitely one of the most important choices that have to be made. And in addition, the actual structure of the MRP model, once the sample has been selected, so this depends highly on the data available and the complexity of the relationship between the survey outcome and the covariates and the weighting variables. And so here I've presented just a very simple bare bones MRP model. But in reality, you would have a lot of interactions between the survey variables and the covariates, and you could use a more flexible model to estimate the prevalence, for instance, instead of using logistic regression as well. And lastly, we have the prior distributions for the parameters, and of course, these are hopefully these would be informed by prior knowledge or some previous seroprevalence studies, but they should be specified. We specify them here to impose some level of prior regularization on the contribution of the covariates, but still allow to vary moderately, just as a demonstration. And in addition, I didn't show here, but we did perform some sensitivity analysis for these prior distributions to show that the simulation results are relatively robust. And so thank you very much. And here are some acknowledgements.